Okay, so I'll be talking about developing models for a 0.8 millimeter coaxial VNA calibration kit within the NIST Microwave Uncertainty Framework. I'd like to start out by acknowledging my co-authors from NIST, Chris Long and Ari Feldman, as well as John Martins from Anritsu. Just a brief overview. As I mentioned, we're developing models for a 0.8 millimeter coaxial VNA calibration kit. First, we created physical models of the commercially available standards and included error mechanisms so we could propagate uncertainties. And then next, we calibrated a VNA with this calibration kit and compared our measurements and uncertainties of two different verification devices that were supplied with the kit, namely a line and also a Beatty line with data provided by the manufacturer. And we found that our measurements agreed to within their respective uncertainties. So the motivation, as everyone here is aware, there's always a demand for faster data transfer rates, and the wireless industry is always developing technology into the millimeter wave spectrum. So typically, waveguides are often used at higher frequencies since they're easier to manufacture and they're less lossy than coax. But the main disadvantage of waveguides is that they're limited bandwidths, so they kind of preclude broadband frequency coverage. So just a quick example here of looking at some different waveguide frequency specifications from WR42 to WR8. You can see you have these little limited frequency bands, which is actually quite useful for a lot of communications applications. But in some applications, you want to have broadband frequency bandwidths. So here you can see some of the different coaxial connector frequency specifications. And for 0.8 millimeter coax, you can go from basically DC to 145 gigahertz. And that's one of our motivations, is because one thing we'd like to do at NIST is we do electro-optic sampling where we calibrate photodiodes that are used as phase standards. And right now we're limited to 110 gigahertz because of our 1 millimeter connectors. So if we could get some photodiodes with 0.8 millimeter connectors, we could increase our capability up to 145 gigahertz. So here's a look at the 0.8 millimeter calibration kit we got from Anritsu. There's basically two sets of calibration standards here. There's male and female open, short, and load standards for frequencies 80 gigahertz and less. And then there's a separate cal kit that's basically 3 pairs of offset shorts that are used from 80 gigahertz to 145 gigahertz. And this cal kit also includes 2 verification devices, a matched line and a Beatty line. And we'll compare measurements of these 2 verification devices. Okay, so Anritsu, for their models, they use these polynomial models, and they're based on measurements taken with a multi-line TRL calibration using 0.8 millimeter connectors, and I was pretty impressed they could do that. I know I don't have good enough eyesight or hand-eye coordination to pull that kind of airline off. But nevertheless, they have, for their offset opens, they have these polynomial models that have effective capacitance that have 4 terms, as well as an offset length. And then for the shorts, they have an effective inductance with 4 terms and a length. And interestingly enough, for their loads, they have an effective capacitance, inductance, and an effective length, which I hadn't seen before. But it gives them a lot of variables that they can play with to model their measured loads. And then they also have like a DC resistance as well. At NIST, we do something a little bit different. We try to develop physical models for our standards. And we can create these physical models within the NIST Uncertainty Framework, which allows us to do VNA calibrations and propagate uncertainties. Here's just an example of a few things that go into a model. using the uncertainty framework. This is basically showing an offset open. So for our offset open, it's like a 2-port open here. We've got an open standard, and then we actually have to cascade coax lines because of the offset shorts, or sorry, for the offset lengths of this open. And then we also have models for the pin depth gaps on both sides. So then so our overall offset open is a cascade of 5 different models. And then the open itself is just a simple open of where you can put in conductance and capacitance. And then the coax line, which represents the offset there, you put in a number of inputs such as your inner conductor diameters, outer conductor diameters, and lengths, and so forth. So here we can create our physical models, and they're all basically based on closed form expressions that have been input into the uncertainty framework. So let's just look at some of our physical error mechanisms for our cal standards. For the 0.8 millimeter, we've got inner conductor diameters, outer conductor diameter, pin diameters and pin depths, et cetera. And ideally, what we'd like is to have all of our dimensional tolerances traceable to NIST measurements in Gaithersburg, but for this particular new kit we have, we don't have that, so we're utilizing the dimensional tolerances that were given to us by Anritsu to create our models. Here's a look at some other error mechanisms for the open, short, and load. They're fairly similar and simple. They have an offset length, and then for the opens we have the capacitance and conductance for the male and female opens, and then we have the same thing for the short. We have an offset length as well as inductances and resistances, and then for the load we also have inductances and resistances. So here's a look at, I'm going to compare the models that we developed in the uncertainty framework to the models that were provided by Anritsu. So here's a model of an open standard up to 80 gigahertz. Here you can see the blue lines are the uncertainty framework and the red are the Anritsu. They don't take into account losses, so we have a little bit of loss here with respect to frequency. And then if we look at the phase and degrees here, as a function of frequency, we can see we match up quite well. And here's a look at a model of the male load standard. Once again, the red line here is Anritsu's, and you can see that they have a lot of degrees of freedom here from their polynomial model, and I believe it's used to basically fit their multi-line TRL calibration of this load. Our load model doesn't have quite as many degrees of freedom, but we match mostly within our uncertainties. And luckily the match is good enough that there's not much of a difference here. It's mostly at reflection coefficients of around minus 40 dB. Then there's also the physical error mechanisms of the offset short standards that are used from 80 to 145 gigahertz. And they're all pretty similar except for different offset lengths. So let me talk about our measurement configuration. It was a little bit strange because we had to use 2 different VNAs. We don't have a VNA with 0.8 millimeter test ports. So what we did was we made use of our VNA that has 1 millimeter test ports, and we have adapters to go from 1 millimeter to 0.8 millimeter. And then we could do that OSLT calibration that's meant up to 80 gigahertz, but since our VNA went up to 110 gigahertz, we thought, well, let's just measure all the way up to 110 and see how that works. Then for the high band with the offset shorts, we had another VNA that had WR8 test ports. So we were able to make measurements on that from 90 to 140 gigahertz. And we had adapters to get us to 0.8 millimeter. So we've got measurements up to 110 for OSLT and 90 to 140 on the offset shorts. So that gave us actually from 90 to 110 gigahertz, we have some overlap, which was kind of nice, so we could see how well our 2 calibrations we're doing. And then in addition to these, calibrating these 2 VNAs with the different calibration kits, we measured our Beatty line and match line on both of these VNAs. So here's a look at the Beatty line. There's a number of curves here. So the Anritsu gave their data from their measurements of these verification devices, and they have it broken up into 2 bands, the low band up to 80 gigahertz, and then there's a high band from 80 to 145 gigahertz, and that's, so I'm showing theirs is red, and then their high band is in pink. And then you can also see their uncertainty bands, and John mentioned to me that their uncertainty bands are very conservative, and they not only include uncertainties in their standards, but they also take into account repeatability and reproducibility. Then we have our measurements in blue and for our high band, or sorry, for our low band measurements, and light blue for our high band measurements. So our blue measurements went up to 110 gigahertz since we had the ability to do that. And then our high band measurements were from 90 to 140. So you can see there's a bit of an overlap here between 90 and 110. And I'll show that in more detail a little bit later. But you can see overall we're getting good agreement with Anritsu's measurements within their uncertainties. And you can also see this is plotting the reflection or S11 of the Beatty line in dB as a function of frequency. Once again, we get good agreement. Here's a look at the matched line. Once again, the red and the pink correspond to Anritsu, and they have a little bit wider uncertainties. Our measurements are a little noisier, but they have lower uncertainties because these are based on basically just one calibration, and we haven't had time to do repeatability studies yet on ours. And here's looking at measurements of S11 of the matched load, so you can see that they compare pretty well as well. On this plot, I'm showing just the NIST measurements on the Beatty line for the S21, and kind of zooming up to show between 90 and 110 gigahertz where we have the overlap, just to see how well our measurements compare. So this dark blue line again is making use of the OSLT calibration, even though it's only specified up to 80 gigahertz, but we made measurements all the way up to 110. And then the light blue one is the measurements using the offset shorts from 90 to 140 gigahertz. And we can see that they compare well between these 2 calibrations, which is reassuring. And also for the matched line, if we look at S21, they agree within their uncertainties. So that's also reassuring. Okay, so that pretty much covers what I wanted to talk about today. So in conclusion, we developed models for a 0.8 millimeter coaxial VNA calibration kit within the NIST Microwave Uncertainty Framework. We found our measurements agreed within their respective uncertainties, both with our overlap and between the NIST and the Anritsu measurements. And some of our future work includes a study of connector repeatability, as well as developing an approach for eventually achieving traceability in terms of dimensional tolerances. So that's all I have, and thanks for your time. Okay, for ours we have physical models of our standards, and each input to our model we have corresponding uncertainties. So for instance, for the offset short, we have some of our uncertainties include the uncertainty in the outer diameter and the inner diameter, as well as yeah, so we have to propagate all these uncertainties from our standards through the calibration to the device under test. And it's pretty easy to do with the uncertainty framework. We can develop physical models, and then it can it can do one of two different types of uncertainty analysis. It can do a sensitivity analysis or a Monte Carlo analysis. And usually for VNA calibrations, it's pretty linear, so you can get away with just a sensitivity analysis. Oh, the constraints? Well, we usually, whatever calibration kit we have, we usually use it for that frequency range that it's specified for. But we kind of experimented with this open short load since it was supposed to be good up to 80 gigahertz, and we went all the way up to 110. But I guess it would be a kind of an application by application thing. I don't know if there's any generalization I could make on that. Oh. Yeah, I usually haven't tried going much past the specifications, but it's definitely an interesting topic. And if somebody else has any experience with that, I'd love to hear about it. Yeah. So you're talking about how can you tell if one of your calibration devices maybe in your kit isn't working right, or? Yeah, that's always difficult. One typical thing to do is perform a calibration and then have some verification devices you can look at. And if you try to keep a history of your verification device, and if it looks like it's out of spec, then you have to start looking a little more carefully. Yeah, if it's like if it's a lumped element kit like open short load, you can try to measure it with a TRL calibration and see if it's giving what you think it is. Yeah, sure.
One quick question. So if you go back to the previous slide, when you say the transfer, I see the difference when you do uncertainty analysis, you reach it like 0.2 dB.
Uh-huh.
Consider this a good agreement? It's everything within the 0.2 dB.
Yeah. Well, whether it's good or not, it's as good as it's what the uncertainties we have give us. These dotted red lines, as I mentioned, are from Anritsu, so they're a little high, but I think they're being very conservative because they're taking into account multiple reproducibility possibilities, or the potential for reproducibility and repeatability if you're making multiple measurements. Yeah. Okay. Thank you.
A few logistics items to note. The exhibits are open as yesterday, along with posters, so down on second floor, again until 10:10. The next session is a joint ARFTG RWW plenary, which is in the rooms behind the exhibits, Lone Star DEF. And then the ARFTG lunch at noon is back on this floor, right across the hall in Texas F. So downstairs for a while, and then back upstairs. Anyway, the plenary starts at 10:10, and then lunch is at noon. Also posters? Posters are also downstairs in the exhibit area as yesterday. And summary sheets, as talked about yesterday, make sure you fill those out and turn them in before the end of the day.